Okay. Let's go ahead and get started. I was going to continue on with the review from the other day. I didn't see any practice final on Brooks. No, okay. There is one on the other instructor's website. I'm also happy to go over or post on Canvas if that's something you shouldn't see. I can definitely do that. Yeah, let's do this, and then we have time when we're looking at it. So let's see, moving right along. Problem 10. Let me do one thing here. Let me this way. Yeah. Okay, problem 10. We want to set up an integral for the area bounded by the following two functions: x equals y squared and x equal to y plus 6. I'm going to do this one without drawing the graph to show you how to do it without drawing the graph, but then I will also draw it to show you how to do that. So if I'm trying to find the area bounded by two functions, I really want to find where they intersect. So I'm going to set y squared equal to y plus 6. I'm just setting the x's equal to each other. And I'm going to bring everything to one side. Y squared minus y minus 6 equal to 0. And hopefully it factors. It does. It factors as y minus 3 times y plus 2. So we get intersection points of y equal to 3 and y equal to negative 2. So what I'm thinking is I have a function, I have something on the right, something on the left, and I'm going to do the integral from the lower y value to the upper y value of essentially the right function minus the left function. If my functions were in terms of x instead of in terms of y, I would be doing the top function minus the bottom function. But since it's in terms of y, we do right minus left. So now I have to figure out which one's bigger. So I'm going to pick a point between negative 2 and 3. Pick any y value between negative 2 and 3. Let's pick 1. Say y equal to 1. Then I'm going to plug that into both functions. So for x equals y squared, we're going to get x equal to 1. And for x equal to y plus 6, we're going to get x equal to 1 plus 6, which is 7. Clearly, this is the bigger one. So x equal to y plus 6 is bigger than x equal to y squared on the interval from negative 2 to 3. So that means our integral should be the integral from negative 2 to 3 of the bigger function y plus 6 minus the smaller function y squared. It is important to note that this problem only said to set up the integral. So definitely pay attention for that on an exam. If the problem says just to set it up, don't do more work than you need to do. Yeah. The other thing, so in case you want to see, we could graph this. If I want to graph x equal to y squared, instead of being an upward opening parabola, it's a rightward opening parabola. So this is the graph of x equal to y squared. You could also think of it as y equal to root x, except it's really y equal to root x or y equal to negative root x. So it's a little harder to graph that way or to think of that way. And then x equal to y plus 6. I'm terrible graphing a line like that. I would really just think of this as y equal to x minus 6. So that's going to look something like this. And then we can see that they have intersection points when y is -2 and the x value would be 4. And this other value here, when y is 3, the x value would be 9. So you can see, oh yeah, if I drew a horizontal strip, it would definitely be the integral from y equals -2 to y equals +3 of the right function minus the left function. So you don't have to draw the picture, but it is helpful to draw the picture. All right, let's do the next one. Again, if you have questions on Zoom or in class, please don't hesitate to ask them. I'm happy to answer any questions. So, problem 11. Let R be the region in the first quadrant bounded by the following functions. Bounded by y equal to the natural log of x equal to 2, and the x-axis, which when you read x-axis, you should be thinking, oh, that's just y equal to 0. Set up, again, set up, right? But don't actually calculate integrals for the volume of the solid formed by revolving the region R about a couple different axes. So let's try first the x-axis. I do think it's worthwhile to draw the picture here. So drawing the region, I have the graph of y equals natural log of x, which has a vertical asymptote here, has an x-intercept of 1, and then keeps going off like this. I have the line x equals 2, so x equals 2 looks like this. And I also have the x-axis, which is right here. Oops. So looking like my region is this little section right here. So I'm going to revolve that around the x-axis. I'm going to draw it again, so I can just kind of have it. So there's my region. I'm revolving around the x-axis. So whatever axis you're revolving around, you want to pick a strip that is perpendicular to that axis. So I'm revolving around the x-axis, I'm going to pick a vertical strip. And then in general, the volume of the thing revolved around the x-axis is the integral of pi times your radius squared times dx. Our strips go as far left as 1, as far right as 2. Our radius is just how far away this end part is from the axis of rotation. Or if you really think about it, right, if you actually think about taking this strip and revolving it around the x-axis, you get this disc shape. And the radius of the disc is exactly just how tall the function is. Which in this case is the natural log of x. So then if we plug that in, we're going to get the volume is equal to the integral from 1 to 2 of pi times the natural log of x squared dx. Not impossible to integrate, but certainly challenging to integrate. It does require integration by parts twice. We don't have to do it, but if we have time at the end, we can come back and do it. It's good practice. All right, let's see. Do we have enough room here? Yeah, we probably have enough room. Let's do B, which is around the y-axis. So similar idea going around the y-axis, but now we're definitely going to use a horizontal strip instead of a vertical strip, right? We want to use a strip that's always perpendicular to the axis of rotation. And unlike before, instead of using the disc method, now we're going to have to use the washer method, because when I rotate this strip around, we're going to get a little hole in the center. In fact, we could draw it. Yep, we can kind of draw it. Kind of draw it terribly. But there's our strip revolved around the y-axis. Definitely there's a hole in the middle. So in this case, instead of being just the integral of pi r squared, it's going to be the integral of pi times the larger radius squared minus pi times the smaller radius squared. This time it's a dy instead of a dx because it's a horizontal strip. And instead of talking about how far left and how far right our strip goes, we have to talk about how low and how high it goes. I think we can see the lowest value of our the lowest y value our strip goes down to is 0. For the highest value, we actually do a little bit of work. So I have to figure out what y value we get when these two functions intersect. So I've got x equal to 2 and y equal to the natural log of x. Well, all I'm going to do is plug in 2 for x and get y equal to the natural log of 2. So this point here is 2 comma natural log of 2. And so the y value would be the natural log of 2. All right. Looking at the picture, I can see that the outer radius is just the function x equals 2. And the inner radius is that logarithmic function, but we have to write x as a function of y. So we can't say it's y equal to the natural log of x. We have to say that it's x equal to e to the y. So y equal to natural log of x, e to the y equals e to the natural log of x, e to the y. Right? If you have a dy, all your functions have to be in terms of y. If you have a dx, all your functions have to be in terms of x. So this one we would write as, I would factor out the pi and write it as the integral from 0 to the natural log of 2 of my big radius squared, so 2 squared minus my little radius squared, which is e to the y squared. You could simplify this. I don't think it's really necessary if you're just being asked to set it up, but if we wanted to do one little simplification, we could. It's the integral from 0 to natural log of 2 of 4 minus e to the 2y. Of the two of these, this one is definitely easier to integrate than the first one. This one's pretty straightforward. The integral would be 4y minus e to the 2y over 2. Plug in. All right. If we have time at the end, we will come back and integrate both of these. The first one is kind of a pain, but we can do it. Any questions about this one? Guys, like, no, we're good. It's all there. Megan and Michelle. All right, Megan and Michelle. No questions? We'll move on. Let's move on to problem 12. Now let's see. Problem 12. A radioactive substance decays from 36 grams to 4 grams in 2 hours. How much is left after 5 hours? So whenever I have these radioactive decay problems or exponential growth or anything like that, I know I'm always starting with the y equal to y naught e to the kt, or if you prefer, y equals c e to the kt. It doesn't matter what constants you use, it's still the same idea. And I always like to make a little table of times and amounts. So I know in the beginning, the time equals 0, I have 36 grams. And now this one we have to be especially careful about because they've used language I think that can kind of be confusing. So often someone will write something intended to be confusing, meaning I could say that I start off with 36 grams and then in 2 hours it decays by so much. Like I could say it decays 10 grams, which would mean that there was 26 grams left. But here they've used the word decays in a slightly different way. They said a radioactive substance decays from 36 grams to 4 grams, meaning that we have 4 grams at this later time. So we can say that 2 hours later, we have 4 grams. Not that it's decayed by 4 grams, it's decayed to 4 grams. So definitely be extra careful when reading these problems. You're always talking about how much stuff you have, not how much stuff you have lost. And here we are talking about, oh yeah, we're starting with 36 grams and we're getting to 4 grams 2 hours later. And so then the question we want to answer is, when it's 5 hours after the initial observation, how many grams are there? I always like to do this. I find it helpful because now I can just plug in this data, find my constants, and then plug in this to find the y value. So let's see what we've got. Plugging in this first data, I'm going to get 36 equal to y naught e to the k times 0. Well, that's going to lead me, not surprisingly, to y naught equals 36. Right? Typically, your y naught or your c is just the amount you're starting with. So then we can rewrite our model as y equal to 36 e to the kt. And then we plug in the other data points. Okay. Now we're going to plug in y equal to 4. 36. And we're plugging t equal to 2. And then we solve for k. So divide both sides by 36, you get 1/9 equal to e to the 2k. Take the natural log of both sides. Natural log of 1/9 equals 2k. Finally, k is equal to natural log of 1/9 divided by 2. So then our fully formed model is y equal to 36 e to the natural log of 1/9 over 2 times t. By the way, so if someone says like find an equation for how much radioactive substance there is at time t, this is what they mean. They mean find the model. This is the equation for how much there is at time t. So then to find out how much there is after 5 hours, we're just going to plug in t equal to 5. So we're going to get y equal to 36 e to the natural log of 1/9 over 2 times 5. And without a calculator, I would leave it like this. Bonus question. What's the half-life of this material? So the half-life is an amount of time, and it's the amount of time it takes until half of it remains. So if I start with 36 grams, I'm really trying to figure out how long until I have just 18 grams. So we're going to set y equal to 18. Basically, to find the half-life, you're always setting y equal to half of the amount that you start with, and then just solving for t. So we're going to get 18 equal to 36 e to the natural log of 1/9 over 2 times t. We're going to divide both sides by 36, so we're going to get 1/2 equal to e to the natural log of 1/9 over 2 times t. We're going to take the natural log of both sides. So the natural log of 1/2 is equal to the natural log of e to the stuff is just the stuff. So we're going to get natural log of 1/9 over 2 times t. And then we'll divide both sides by this. So not surprisingly, just to point out, the half-life for t is going to be t equal to the natural log of 1/2 divided by this k value, which is very typical, right? If you've ever taken a chemistry class, you've probably seen something like that. You might have seen it as natural log of 2 divided by k, or maybe negative natural log of 2, depending on, some people like to throw in the extra minus sign to make it more confusing. But we're getting t equal to 2 times natural log of 1/2 divided by natural log of 1/9. Kind of want to calculate it just for point, to kind of to see if it makes sense. So right, definitely we think the half-life is going to be pretty short because in just 2 hours we've decayed all the way to 4 grams. So the half-life is probably going to be something like, I don't know, a half hour, maybe even less. Let's find out. Let's see, 2 times natural log of 1/2. I still can't believe that I can find the natural log button on this. I was like, it's right there. I was like, how could I not find the natural log button? It's killing me. Okay. We get about 0.63 hours. So a little more than half an hour. My guess was pretty good. All right. Let's move on to the next thing. Find K. Not the same kind of K. Find K so that this function, f of x equal to k times x times the cube root of x minus 1 is a PDF on the interval from 0 to 1. Okay, so if you want something to be a PDF, the integral of it has to equal to 1. So we're going to set the integral from 0 to 1 of k times x times the cube root of x minus 1 dx equal to 1. And you could kind of, if you really wanted to kind of see something here, you could pull out the k and say k times this integral is equal to 1. So k is really going to equal just 1 divided by whatever this integral is. So I might just drop the k and do this part separately is what I'm trying to say, I guess. So k is definitely going to be 1 over the integral from 0 to 1 of x times the cube root of x minus 1, which we'll figure out what that is in a moment. So let's just do the integral without bothering with all the k and setting it equal to 1. It just feels like it's a little bit easier to manage. All right, so the integral of x times the cube root of x minus 1, it's not a mixture. So I'm kind of thinking u sub, right? Like I don't really have any other options here. I can't multiply it out. I can't use integration by parts. Can't use partial fractions. It's definitely not on the table, right? There's just not a lot of options here. I really think the only option is letting u equal the only kind of thing that makes sense, which is u minus x minus 1. That works out in some sense in that, well, du is dx, so changing the dx to du isn't a problem. But then I have this leftover x, so we're going to have to do a back substitution. So x is equal to u plus 1. So this integral is going to become the integral of x, which is u plus 1, times the cube root of u du. And personally, I think we should change the limits of integration. So instead of going from x equals 0 to x equals 1, let's say, well, if x equals 0, then u equals 0 minus 1. And if x equals 1, then u equals 1 minus 1. So my limits of integration, instead of going from 0 to 1, are going to be going from u equals -1 to u equals 0. And I really, really recommend doing it this way. I just think it's a little bit better. You don't have to, though. Do whatever you want. I just think this is the better one. Right. So then we're going to rewrite this as the integral from -1 to 0 of u plus 1 times u to the 1/3, and then distribute the 1/3. So the u to the 1/3. So I'm going to get the integral from -1 to 0 of u to the 4/3 plus u to the 1/3. Now we're going to integrate. We're going to get u to the 4/3 plus 1 is 7/3. Dividing by 7/3 is the same as multiplying by 3/7, plus u to the 4/3 times 3/4 from -1 to 0. When we plug in 0, we're going to get 0. When we plug in -1, let's see. -1 to the 7/3 power. What is -1 to the 7/3 power? Is it -1 or is it positive? Let's see. The cube root of -1 is still -1, and -1 to the 7th power is still -1. So we're going to get a 3/7 times -1. But then when I plug in -1 to u to the 4/3 power, -1 to the 4/3 power is the cube root of -1, which is -1. But then -1 to the 4th is +1. So here we're going to get plus 3/4 times 1. Which is a little worrying. Yeah, that's very worrying. It looks like I'm getting a negative value. Looks like I might have made a mistake somewhere. Let's double check. So let's see. So let's make sure I've read the problem correctly. So this is actually this is good to think about. So if you see what's going to happen here, if I keep going, I'm going to get negative, so positive 3/7 minus 3/4, and that's definitely negative. And k shouldn't be negative, right? So what's going on here? Let's take a look. So I let u equal x minus 1. My du is dx, my x was equal to u plus 1. And then I change my limits of integration. If x is 0, u is 0 minus 1. If x is 1, u is 1 minus 1. Okay, so negative 1 on the bottom, 0 on the top. U plus 1, u plus 1, u to the 1/3. Distribute that, you got u to the 4/3, u to the 1/3. Okay. And then integrate this, u to the 7/3 times 3/7, u to the 4/3 times 3/4. Plug in 0, you get 0 plus 0. Minus, plug in negative 1, you get 3/7 times negative 1 plus 3/4 times positive 1. I don't see what's going on here. Let's see. I do have the answers though, so that's good. Let's double check. Oh, no. You do get k equal to a negative value. That's weird though. I guess, yeah, oh yeah. I guess I wasn't thinking about that. I was thinking of the cube root being positive. Yeah, you're right. You're right. So this cube root, good observation. Yeah. So from 0 to 1, the cube root of x minus 1 is negative. So then it does make sense that k should be a negative value. Okay, so k can be negative. So we end up getting, let's see, 4 times 3 is 12, 28. 7 times 3 is 21, 28. So I end up getting negative 9, 28. So k is negative 28/9. Yeah, I guess that works just fine. It's just kind of funky. So our PDF, just to point out, our PDF is f of x equal to negative 28/9 times x times the cube root of x minus 1. And this function is positive on the interval from 0 to 1, as a PDF should be. Okay. So don't let your preconceived notions get you confused, right? He says to himself. Yeah, it's not that k has to be positive, it's that the function overall has to be positive on the interval. All right, let's go 14. Find the standard deviation of the PDF f of x equal to 9/4x cubed on the interval from 1 to 3, if we already know that the mean is equal to 3/2. Well, how helpful that is. So a reminder, there are two ways of calculating the standard deviation. Really though, I'm not really going to calculate, I mean I am, but I'm going to calculate the variance and then take the square root of it. So there's two ways of calculating the variance. The variance of x you can either do as the integral over the entire interval of x minus your mean squared times your PDF. That's one way of doing it. Or the preferred way, we can calculate the variance as the integral from 1 to 3 of just x squared times your PDF, and then minus your mean squared. And hopefully all of you can see that this second way of doing it is going to be way easier, right? X squared times 9/4x cubed simplifies really nicely. X minus 3/2 quantity squared times 9/4x cubed. We're going to have to integrate 3 different things if we do it that way. So definitely this is the way to go. We're going to end up getting the integral from 1 to 3. I'm going to factor out the 9/4. And x squared over x cubed reduces to 1/x. Minus 3/2 squared is also 9/4. So then we get 9/4 times the integral from 1 to 3 of 1/x. Well, that's just the natural log of the absolute value of x from 1 to 3. Minus 9/4. So then they end up with 9/4 times the natural log of 3 minus the natural log of 1 minus 9/4. So I end up with 9/4 times the natural log of 3. I'm factoring out the 9/4 to say it's 9/4 times natural log of 3 minus 9/4, which is 9/4 times natural log of 3 minus 1. So that's our variance. And then the standard deviation is the square root of that. Which I suppose we could square root 9/4 and say it's equal to 3/2 times the square root of the natural log of 3. I do want to make it extra clear that this really is the way you should do it. If you happen to try going the other way, it'll work going the other way. It's just a lot more work. So if you do it this way, it's the integral from 1 to 3 of x squared minus 3x plus 9/4 all times 9/4x cubed. And then you have to distribute that to each term. So you have to integrate from 1 to 3, 9/4x minus 27 over 4x squared plus 81/16 over x cubed. Right, that just seems like a lot more work. So definitely don't do it this way. Do it the nicer formula way. Right. Let's go to the next one. 15. At the MU Coffee House, the Coho, the wait time to buy a cookie go for a cookie right now. Sounds good. Is modeled by the PDF f of x equal to 3 over x plus 2 squared, where x is between 0 and 4. So at the shortest, you're waiting 0 minutes. At the most, you're waiting 4 minutes. Question A, what's the probability of having to wait 1 to 2 minutes? Well, the way we write that, or one way of writing that, is the probability that x is between 1 and 2. It doesn't matter if you have greater than or equal to signs or just strictly greater than signs. Integrals don't care about whether or not you're actually equal to 1 or not. Either way, it's going to be the integral from 1 to 2 of this function. I would probably rewrite it as the integral from 1 to 2 of 3 times x plus 2 to the negative second. You certainly could do a u sub here, but it's not super necessary. We could just say it's going to equal 3 times x plus 2 to the negative first divided by negative 1. 1 to 2. If you wanted to, right, the u sub would be u equal to x plus 2, du is dx. So then the integral of 3 times x plus 2 to the negative 2 dx becomes the integral of 3 times u to the negative 2 du. And then you integrate, you get 3u to the negative 1 over negative 1, and then you get 3x plus 2 to the negative 1. I really prefer to rewrite this. I would write this as negative 3 over x plus 2 from 1 to 2. And then plugging in, we get negative 3 over 2 plus 2 minus negative 3 over 1 plus 2. So I end up with negative 3/4 plus 1, which is 1/4, or 0.25. So there's a 25% chance that it's going to take between 1 and 2 minutes to get a cookie. Which might feel like, well, James, you might be thinking to yourself, or someone might be thinking, well, James, clearly, of course, it's 1/4 because it's 1 minute out of 4 minutes. That's not true, right? If it was instead, so let's just to kind of dissuade someone from thinking that, what's the probability that's going to take between 0 and 1 minute? So that would be the integral from 0 to 1 of the same thing. And here's the nice thing about doing this question more than once. We already know what the integral is, right? We know that the integral is negative 3 over x plus 2 from 0 to 1. You plug in 1, you get negative 3 over 3. You plug in 0, you get negative 3 over 2. So I've got negative 1 plus 3/2, which is positive 1/2. So there's a 50% chance that it's going to take 0 minutes to 1 minute. There's a 25% chance it's going to take 1 minute to 2 minutes. I don't know what it is for 2 to 3 or 3 to 4, but you could find it if you want to. But I just want to really stress, right? It's not just because it was 1 minute out of 4. It's because we did the integral and it happened to be 1/4. Let's find the average and the median wait time. So median wait time. I feel like median is the one that always people kind of puts people off. That's where we do the integral from your lower bound to the middle, which we don't know. So we're going to go from 0 to m of 3 over x plus 2 squared dx. That should equal 1/2. Here's what I know just from the work I did already. I know the median is going to be somewhere between 1 and 2. Oh, actually, you know what? I already know what the median is going to be. I happened to find it in the previous problem. So I made up an extra problem for this one. So it's still worth doing this work, but we can see from the work we did right there in part B that if the probability of taking between 0 and 1 minute is exactly 1/2, 1 minute is going to be the median because 1 is the cutoff from, right, if my function looks something like this, what we just found was that right here, 1/2 of the area is over there. So it has to be true that 1/2 is also over there. It's still worth doing this. So if we were doing this, we would say, all right, integrate this. We know it's -3 over x plus 2 from 0 to m equal to 1/2. And then we're just going to plug in and solve for m. So we get -3 over m plus 2 minus -3 over 0 plus 2 equal to 1/2. I would subtract 3/2 from both sides. So you get -3 over m plus 2 equal to 1/2 minus 3/2, which is -1. So -3 over m plus 2 equals -1. M should equal 1. I mean, we can do the work, I guess, fine. -3 equals -1 times m plus 2. -3 equals -m minus 2. -1 equals -m. So m equals 1. So we already knew. So that's how you find the median, right? You take so I should point out, typically, most people, if your interval is from A to B, they usually do from A to M, but you could do from M to B if there was a good reason to do that. Maybe someone's giving you a really stupid PDF from like -∞ to 0, and it's much easier to do the middle to the 0 than it is from the -. Usually we use the lower one, but really whatever is more convenient is what you should use. Okay, let's look at part D, which is the average wait time. So that's where you integrate x times your PDF. So the integral from 0 to 4 of x times 3 over x plus 2 squared. Oh, that's an interesting looking problem. I think we can either do a U sub or partial fractions. If I have my choice, I'm going to do a U sub. But I will point out, right, you could do partial fractions. You could think of this as 3x over x plus 2 squared. I don't think you need to do partial fractions. Let's do a U sub. So u is equal to x plus 2. Du is dx. I'm going to have a back substitution. X is going to equal u minus 2. I would probably also factor out the 3. So this is going to equal 3 times the integral of, so x is u minus 2, and x plus 2 is equal to u. And my new limits of integration, if x is 0, u is going to be 0 plus 2. If x is 4, u is going to be 4 plus 2, which is 6. So then simplifying, we have 3 times the integral from 2 to 6 of u divided by u squared is 1 over u. And 2 divided by u squared is 2u to the negative 2. Integrating, the integral of 1 over u is the natural log of the absolute value of u. The integral of minus 2u to the negative second is minus 2u to the negative 1 over negative 1. So we end up with 3 times the natural log of the absolute value of u plus 2 over u. And then plugging in our limits of integration, we get 3 times the natural log of 6 plus 2/6 minus the natural log of 2 plus 2 over 2. To definitely simplify that, the natural log of 6 minus the natural log of 2 is the natural log of 3. And 2/6 minus 1 is going to be 1/3 minus 1, which is negative 2/3. And then I suppose you could distribute the 3 and say it's 3 natural log of 3 minus 2. I don't think all that's necessary, right? If I was taking a test, I definitely would probably stop like at this first step here. I wouldn't do all this extra simplification unless I had time at the end to do it. But that is what you could do. I'll check one thing. Yeah, definitely. So certainly in the solutions, right? The person writing solutions definitely did not simplify it further, and I think that's the right call. Right on the test, simplifying. I mean, unless Dr. Burke, I don't think Dr. Burke is really like, I don't think she's like simplify. Like I feel like she is also of the mind that yeah, you should do the work until you've gotten to an answer. And then sure, if you have all the time in the world at the end, go simplify things, but I would probably not. All right, a couple more examples here. Let's do 16. A 2-sided coin is tossed. And that's funny. What other kinds of coins are there? I don't think there's a 3. I've never seen a 3-sided coin or a 1-sided coin. Mobius strip of a coin. Okay. So a coin is tossed 3 times in succession. 3 times in succession. So 3 coin tosses in succession. Let x equal the total number of tails. Find the probability that x is greater than or equal to 1. So there's a couple ways of doing this. The idea really here is that instead of finding, so the probability that x is greater than or equal to 1 is the probability of getting 1 tail plus the probability of getting 2 tails plus the probability of getting 3 tails, which is not super hard to calculate. Right? We could totally just write this one fully out, but if instead of like 3 coin tosses, it was 10 coin tosses, it would be really hard to calculate this. In fact, let's make it 10 just to make it a little more interesting. So if I want to find the probability that x is greater than or equal to 1, that would be the probability x equal 1 plus 2 plus 3 plus all the way to 9 and 10. The point of this question is that we can say, or it's going to equal 1 minus the probability that x equals 0. That's really what they're getting at with this kind of question. So what's the probability of getting 0 tails? Well, there's only one way of getting 0 tails, all heads. So there's only one way of getting all heads. How many total different things can happen if you flip 10 coins? Is that what I'm saying? It's a little more than 20. That's actually a lot more than 20. So every coin flip, there's 2 possible outcomes, a head or a tail. So on the first flip, I can get heads or tails. On the second flip, heads or tails. And so on and so on. So after 1 flip, there's 2 possibilities. After 2 flips, there are 4 possibilities. Heads, 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 tails, tails, heads, tails, tails. After 3 flips, there's going to be 8 possibilities. So every time you flip another coin, you double the number of possible things that can happen. So there are actually 2 to the 10th ways of flipping 10 coins. Or if we go back to the previous example, if it was actually 3 coins, then 1 minus the probability of x equal to 0, there's exactly 1 way of flipping 3 heads out of 8 ways of flipping the 3 coins. We can actually write all 8 ways down. You could have heads, heads, heads. You could have heads, heads, tails, or heads, tails, heads, or tails, heads, heads. You could have tails, tails, heads, tails, heads, tails, heads, tails, tails, or we could have all tails. So we can see that there are 8 possibilities and only one of those doesn't have any tails. So the probability of at least one tail is 1, 2, 3, 4, 5, 6, 7 out of 8. So, but generally, if you're flipping some number of coins, the total number of possible outcomes is 2 to that number. Yeah. Let's look at the next part. What's the expected value? So expected value is usually easier to calculate when it's a PDF versus this discrete probability situation. So expected value so for an integral, it's the integral of x times p of f of x dx. For a discrete probability like this, it is the sum of all the values of x times the probabilities of x. So in this case, we can have x equal to 0, x equal to 1, x equal to 2, x equal to 3. So we're just going to take each of those values of x, where x is the number of tails, and multiply it by the probability that happened. So you get 0 tails with a probability of 1/8. Yeah, we're going back to the 2 points. This question would be hard to answer in this way with 10 points. There's another way of answering the question, which I'll mention here, but yeah, if you were going to try and actually calculate this for 10 coins, it would be kind of a giant pain for that. And then probability of getting 1 tail is 3/8, and then for 2 tails, the probability is also 3/8, and then for 3 tails, the probability is 1. So if we add this all up, we're getting 0 plus 3/8 plus 6/8 plus 3/8. We're getting, let's see, 3 plus 6 plus 3 is 12/8, which reduces to 3/2. Now I know you can't get 1.5 tails when you flip 3 coins, but that's not what that means. It means that over the course of time, right, if you keep flipping 3 coins, on average, you will get 1.5 tails. Now, what this also means, or one other thing to see here, at least when it comes to flipping coins, is when you're flipping coins, as long as you're flipping fair coins, the expected value E of x is just equal to 1/2 times the number of flips. Right? If you flip 10 coins, you would expect to get 5 tails on average. That's not mean you're going to get 5 tails every time, but on average, if you keep flipping 10 coins over and over and over again, most of the time you're going to get 5, and it's going to cut. It's going to be close to 5. It's hard to be far off to 5. This also works if you have an unfair coin. So if someone says like you have an unfair coin that's weighted so it comes up heads 1/3 of the time and tails 2/3 of the time, you can find the expected value by just multiplying the probability of getting whatever you want by the number of flips. It always works. It's kind of neat. So yeah, if I was going to do what's the expected value for 10 coins, instead of doing 0 times the probability of 1 plus 1 times the probability of 1 plus 2 times the probability of 2, and so on and so on for all the way up to 10, you'd be like, oh, it's just going to be 10 times 1/2. What's the standard deviation? So standard deviation, we find the variance, and just like the integral formula, there is a nicer formula for the variance using the sum. So you could either do the sum of each x score minus the mean squared times the probability of each x score, or you can do the sum of each x score squared times the probability, and then you can subtract off the mean squared. Either way is correct. I usually find this way to be easier. So doing it the second way, we're going to get, so let's see, we're going to get 0 squared times the probability of 0 plus 1 squared times the probability of 1 plus 2 squared times the probability of 2 heads, plus 3 squared times the probability of 3 heads, 3 tails, sorry, minus the mean, which is 3 halves, squared. So we're going to get 0 plus 3 eighths plus 12 eighths plus 9 eighths minus 9 fourths. 3 plus 12 plus 9 is 24. So we're getting 24 eighths minus 9 fourths. 24 eighths reduces to 12 fourths minus 9 fourths, which is 3 fourths. So then the standard deviation is the square root of 3 fourths. Or you can do it the first way. Right, the first way, it's not that much harder. First way, it would be 0 minus 3 halves squared times 1/8 plus 1 minus 3 halves squared times 3/8 plus 2 minus 3 halves squared times 3/8 plus 3 minus 3 halves squared times 1/8. There is a little more symmetry doing it this way. 0 minus 3 halves squared is 9 fourths times 1/8. 1 minus 3 halves is negative 1/2 squared is 1 fourth times 3/8. And then we get the same thing over here. 2 minus 3 halves is 1/2. 1/2 squared is 1 fourth times 3/8. And here we get 3 minus 3 halves, which is 3 halves squared is 9 fourths times 1/8. So we end up with 9 over 32 plus 3 over 32 plus 3 over 32 plus 9 over 32. So we end up with 12. We end up with 24 over 32, which is indeed 3 fourths. So either way is fine. It just depends on what feels more comfortable. Couple problems going way back. So some derivatives. I know it's been like forever since we talked about derivatives, really. Let's differentiate the following. Differentiate. Y equal to the natural log of x to the 4th times sine squared of 3x over e to the 4x times the square root of 5x plus 6. And the intention here is that you use the rules of logarithms to simplify this expression before differentiating it. So first, we're going to rewrite a few times. So we're going to have y equal to the natural log of the top minus the natural log of the bottom. But then, when you have the natural log of a product, you can break that up into the natural log of one piece plus the natural log of the other piece. So I can rewrite this as the natural log of x to the 4th plus the natural log of, I'm going to rewrite sine squared of 3x as sine of 3x quantity squared. Minus, I can break this up as well. So be careful here. It's minus everything. It's minus the natural log of e to the 4x plus the natural log of 5x plus 6 to the 1/2 power. Right, it is minus each of these things. So that minus sign actually distributes. So typically when I start a problem like this, I always observe that when I break it up, I have 1, 2, 3, 4 factors and with 1, 2, 3, 4 logarithms. The factors on the top have logarithms with positive coefficients. The factors in the bottom have logarithms with negative coefficients after I distribute that. So then one more rewrite, bring down the 4 times natural log of x, bring down the 2 times natural log of sine of 3x, minus bring down the 4x, you get 4x times the natural log of e. But the natural log of e is just 1. And bring down the 1/2, you get 1/2 natural log of 5x plus 6. And now we're finally ready to take the derivative. So dy dx, or y prime, whatever you like, is going to be 4 times 1 over x plus 2 times, okay, the derivative natural log of some stuff is 1 over the stuff times the derivative of that stuff. And the derivative of sine of 3x is cosine of 3x times 3. The derivative of 4x is 4. Oh, that's look, look. So this really does drive home the point that you have to be extra careful. I even said at length this minus sign distributes, and both things should be negative, and then I forgot to do it. All right, at least that looks like a plus sign to me. It should be a minus sign. Minus 1/2 times the derivative of the natural log of 5x plus 6 is 1 over your stuff times the derivative of your stuff. And again, if I were strapped for time, I would leave it like that. If I had all the time in the world, I would probably do some mild simplification. I'd write this as 4 over x. I'd write this as 6 times cotangent of 3x, because cosine of 3x over sine of 3x is cotangent of 3x. Minus 4 minus 5 over 2 times 5x plus 6. That's how I'd want to simplify it if I had the time to do so. Okay. Look at the next one. I think this next one is a special example of something weird, but that's fine. So, oh no, I'm thinking it's something else. Okay. So the next function we want to differentiate is y equal to the natural log of x to the x. Whenever you see an exponential function where the base and the exponent both have variables, this is when we need to use the process of logarithmic differentiation, where we take the natural log of both sides. So start with the natural log of y equal to the natural log of x to the x. I will point out, just as a quick aside, this is not the same. This is not the same as y equal to the natural log of x to the x. Right? If we had that, we could just bring the x down to the get-go and take the derivative straight away using the product rule. But that's not what we have. So right, if you wanted this, you'd have to write it like this, where the parentheses go around x to the x like that. So those are very different things. So now we bring down the x, and we have that the natural log of y equals x times the natural log of the natural log of x. And now we're going to differentiate both sides. The derivative of the natural log of y, I know it's been a while, but y is a function of x. Its derivative is 1 over y times the derivative of y. Or 1 over y times y prime. And then the product rule has to be applied on the right hand side. So we're going to get, if we think of, right, this is our f and this is our g, we're going to get the derivative of f, which is 1, times g left alone. So there's our f prime g. Plus, then we need to flip it and get the derivative f left alone times g prime. So f is just x. And the derivative of the natural log of the natural log of x. So the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And the derivative of the inside stuff is 1 over x. So definitely, there's a couple things we can do here. Well, first of all, I can cancel these x's. Second of all, we need to multiply both sides by y, which I think can be a one-step process, but we can do it in two if you want. So dy dx equals y times all this stuff. So it's y times natural log of x plus 1 over natural log of x. And then I think you could have done this as well at the same time. We need to substitute back in what y is actually equal to. So y is equal to the natural log of x. So dy dx equals, sorry, y is equal to the natural log of x to the x. So dy dx is the natural log of x to the x times all this stuff. And that's your final answer. A little funky. All right, last one on this final review. 18. Interesting. Got something written on the other side. Sure. So find and classify the relative extrema of y equal to x to the fourth times e to the negative 2x. Okay. So step one, find the derivative. So dy dx is equal to product rule again. So it's going to be 4x cubed times e to the negative 2x plus x to the fourth times e to the negative 2x times negative 2. And so whenever you do, so if we're finding the critical values, we're going to set this equal to 0. Typically, the best way to solve this is by factoring as much as possible. So I can definitely factor out an x cubed from each piece, an e to the negative 2x from each piece, and a 2. So I'm going to factor out a 2x cubed e to the negative 2x. Here I'm left with a 2. And here I'm left with a negative 1 times an x. So it looks like I've got 2x cubed e to the negative 2x times 2 minus x equal to 0. So one of my critical values is x equal to 0, because 0 cubed will be 0. And the other critical value is x equal to 2. Basically, I'm just finding all the ways this whole thing can be 0. So either x cubed can be 0, which means x is 0, or 2 minus x can be 0, which means x is 2. E to the negative 2x can never be 0, it's always positive. E to the anything is always positive. All right, so then we have to classify them. This is where we're going to draw the number line, put our derivative on there, f prime or y prime, whatever you want to call it. It's y prime, sure. And then I'm going to put 0 and 2. This is why it's also really important to have the factored form. The factored form makes it really, really easy to tell if my derivative is positive or negative. So here's my derivative again. If I pick a number larger than 2, like 3. I plug in 3. 2 times 3 cubed is positive. E to the anything is positive. And 2 minus 3 is negative. So I have a positive times a negative, which means overall it is negative. Which means my function is decreasing. Between 0 and 2, I'm going to pick 1. 2 times 1 cubed is positive. E to the anything is positive. 2 minus 1 is positive. A positive times a positive times a positive is positive. Which means my function is increasing. Finally, pick something like negative 1. Negative 1 cubed is negative. E to the anything is positive. 2 minus negative 1 is positive. So I have a negative times a positive times a positive. So it looks like we have a relative maximum at x equal to 2, because the function goes from increasing to decreasing. And we have a relative minimum at x equal to 0. All right. So I think give you back 15 minutes of your life. Unless you really want me to do more stuff, I certainly. If you have, are there any questions you'd like? Totally, yeah. Like finding and classifying relative solutions. Sure. Let me see if there's one on this other practice exam. Otherwise, I can just make one up. It's not like hard to do. Oh, it's back pages too. The back pages. So let's, I don't know, what's a good example? I know I've got it. Yeah, okay, let's do this one. So let's same kind of question. Find, classify relative extrema for x equal to that. Let's do that. Let's do x squared times e to the negative x. So, same idea. Taking the derivative, it's going to be 2x times e to the negative x plus x squared times e to the negative x times negative 1. Set that equal to 0. I would probably rewrite this. It's 2x e to the negative x minus x squared e to the negative x. So we can factor out an x e to the negative x. And factoring is definitely like the key thing to see here. So factor out an x times e to the negative x. We're left with a 2 here and a minus x here. Problem looks very similar to the previous one. It is very similar. We get the same critical values actually. So my critical values are x is 0 and x is 2. So then we're going to use the number line. I mean, for the problem to be quite so similar, but and we're looking at the positive or negativeness of the derivative on this number line. So if I pick a number larger than 2, like 3, I get 3 times e to the negative third times 2 minus 3. Positive, positive, negative. If I plug in something between 0 and 2, like 1, positive, positive, positive. If I plug in something less than 0, like negative 1, negative, positive, positive. So this function is decreasing, then increasing, then decreasing. So we definitely have a relative minimum at x equal to 0. And we have a relative maximum at x equal to 2. So I know it's like exactly the same as the previous problem. I know it is a different function actually, but yes, we're getting the same sort of results. We can do another one. Okay. Make it something a little different. Oh yeah, we can go that way. Sure. Let's see. Relative extrema for f of x equal to, let's see, I think, yeah, let's do x squared over x minus 2. It'll probably work out all right. So as usual, gotta find the derivative. So the derivative here, we have to use the quotient rule. The bottom times the derivative of the top minus the top times the derivative of the bottom all over the denominator squared. And definitely is, so I know most of the time we're like, don't worry about simplifying. For these sorts of problems, it really is necessary to simplify as much as possible so we can kind of see what things look like. So simplifying this, we have 2x times x, 2x times x, 2 is going to be 2x squared minus 4x minus x squared over x minus 2 squared. And then simplifying again, I get x squared minus 4x for x minus 2 squared. And then one more time, I'm going to factor out an x. I've got x times x minus 4 for x minus 2 squared. And the critical values are where this is either equal to 0 or undefined. So what are my 3 critical values here? 0, right? Now, here's the thing about 2. 2 is important to include on the number line, but 2 is not really a critical value. And the reason it's not really a critical value is because it's not in the domain of the original function. If you try plugging in 2 into the original function, it's undefined. It's still important to include it on the number line though, because the sign of the derivative might change there. So it really, really is important that we include it. So let's look at our sign chart for our derivative. Putting 0, 2, and 4. So once again, I'm just going to pick numbers in each of the sections. If I pick something like 5, plug into my derivative, I get 5 times 1 divided by 3 squared. Or as I would really say, a positive times a positive divided by a positive is positive. Pick something between 2 and 4, like 3, I get a positive times a negative divided by a positive. It's negative. Pick something between 0 and 2, like 1, positive, negative, And even though the x minus 2 would be negative, it's x minus 2 squared, so it's gonna be positive. So it's still a positive times a negative times a positive, so it's gonna be negative. Finally, being something less than 0, like -1, it's gonna be negative times a negative over a positive, so it's gonna be positive. Another way of doing this is just looking at the powers. So since those have first powers, since 4 came from a factor that's to an odd power, the sign's going to change when you go over 4. Since 2 came from a factor with an even power, the sign's going to stay the same. Since 0 came from an odd factor, the sign's going to change. That's another way of doing it. So this function's increasing, decreasing, decreasing, increasing. So we could say that we have a relative maximum at x equal to 0, and a relative minimum at x equal to 4. All right. It's been a good quarter. Look on your finals. I'll be in drop-in today at 3, and then your finals tomorrow at 10, 10:30. I'll be in drop-in tomorrow at 10. I don't imagine you. I wouldn't encourage anyone to be studying at 10. I would say you should stop studying by 10 tomorrow and give your brain a little mental break so it can rest up before you have to take your final. Good luck. Hope it goes well. I think it will. You're very welcome, of course. Bye.